Three, two, one, let's go. Time for the action. Alright, so last time we set up the exciting world of differential equations, and now we're going to start solving them. So let's get to it. Alright, so what do we know? Well, something we talked about is the general solution to y prime equals 2y is c times e to the 2x, right? This is a first order, there's only one derivative, differential equation. As we discussed, derivatives do not uniquely identify functions, but they do it up to a constant, hence the undetermined constant c right here. Okay, right, and as we mentioned, we know from calculus that this is going to work. The only thing whose derivative is itself is e to the x, thus the only thing whose derivative is twice itself must be e to the 2x by the chain rule, and there we go. But why? Right, I keep saying from calculus we know this is true, but right, why? How do you really go about deriving this? Okay. So let me go ahead and change something. Let me change the differential equation from its Newton notation to its Leibniz notation. All right. So, calculus was created simultaneously by Newton and Leibniz. Sort of this classic example of what's the name of it? Concurrent thinking, I think that's the word for it. Right, where basically there was all of like the foundations, all the ingredients we needed to create calculus were there, and sort of Leibniz and Newton figured it out roughly at the same time. There actually was kind of a big debate as to who should really get credit, because Newton had actually figured it out earlier than Leibniz did, but Newton didn't tell anybody. That's because Newton spent all of his time doing alchemy, and the whole calculus thing was just like, yeah, whatever, I'm just doing that on the side. The real thing I'm going to be doing, I'm going to, convert lead into gold, watch me. But anyway, so Leibniz, though, I feel, as history's gone on here, has gotten a bit more favor. At the time, he kind of got called a hack fraud, but I feel like over the years, Leibniz is the one who's winning out, because his notation for the derivative has something to it that Newton's doesn't. Well, Newton's notation is nice and sleek. Leibniz's notation lets us do something, and that's treat the derivative like it's a fraction. Right, so dy dx, if I pretend for a moment it's a fraction, I can multiply the dx to the other side. Now, note here, this is a differential form, so hopefully you vaguely remember these from calculus. Now, treating it like a fraction lets me do this move. And now if we look at this, that y is, he's feeling a little lonely. He's got the 2, he's got the dx, his buddy dy is over here. So that y wants to get over to the other side of the equation. So let's help him out, get him over there. So now I've got 1 over y dy is equal to 2 dx. And that is begging to just be integrated, right? You're looking at that, you're like, I want to slap some integrals on this thing. So let's do that. All right, so if we integrate, what's going to happen? Well, on the left-hand side, I'm going to pick up log of y plus some constant, and on the right-hand side, I'll pick up 2x plus some constant. Well, I got a constant on the left and a constant on the right, so if I move one of the constants over, then I've just got a constant on one side. So, yeah, whatever, we'll get that and call it a day. Right? Log of y is equal to 2x plus c. Boom, there we go. That is an implicit solution to our differential equation. All right, well, let's not be lazy. Let's actually go ahead and solve it. Now, before we do that, there's some provisos, so some ins, some outs, some what have yous. When I did that integral, I really should have done log of the absolute value of y. Right, and the reason for that is 1 over y is defined everywhere except for y equals 0. So we would like its antiderivative to be defined everywhere other than 0, but log, which we know gives me a derivative of 1 over y, is only defined for strictly positive numbers. So to remedy this issue, usually we slap an absolute value on the log. Now, in practice, we'll always get rid of the absolute value at some point, so whatever, let's just not even include it. And it's worth noting that usually this is not a problem. This may come back to bite us in the ass in a little bit, but let's just say for now we're good. Okay, so I've got this implicit solution, and I can do one better. right? Now, there are going to be implicit solutions where we'll just call it and go like, that's good, that works. But if we can make it explicit, we should always do that. So I'll exponentiate both sides. So exponentiating jailbreaks the y out of the log. On the right-hand side, I'll have e to the 2x plus c. All right, well, that's a summation and the power, so I can split it up as follows. Now, this e to the c, I moved it to the front, which I can do. E is a constant, 2.7 something. C is a constant, don't know what it is, undetermined. Beats me. If I had some initial conditions, I could tell you. This is a constant raised to a constant. So it's a constant, right? It's not variable, like 2x is. Does not involve the independent variable. So we'll simply just go ahead and say e to the c. Well, the c absorbs the e, right? And we'll just replace it with a c. And thus begins the constant abuse of differential equations. All right, so with that said, e to the c is replaced with c, and thus we now arrive at our nice, explicit, general solution to y prime equals 2y, which we now have concrete evidence is equal to c times e to the 2x. All right, nice. All right, so let's formalize this. So we had an explicit example of it. Was there anything special about the right-hand side being 2y? Not particularly. In fact, if you have any first-order differential equation where we've got the derivative on the left-hand side, dy dx, and on the right-hand side we've got f of x times g of y, so we can separate my variables by multiplication, then I can always form an implicit solution by solving the following integrals and setting them equal to each other. All right, beautiful. So, something to notice about this method, integral of f of x dx, pretty nice. Integral of 1 over g of y. So our experience of integrals should immediately start making us feel a little woozy. We're going to go, ooh, 1 over something and trying to integrate that? Ew. So here's where implicit becomes the thing we like. Because a lot of times in practice, the thing on the left-hand side here, this 1 over g of y, sometimes it's not as nice as we'd like it to be. All right. But regardless, this is how we can solve it, so let's give it a go. Okay, so let's consider this. Now, we have got dy dx is equal to 2xy squared minus 4y squared, so if I'm going to read this equation, I want to find the function y whose derivative is equal to itself squared times 2x minus itself squared times 4. All right, so what function has this property, that its derivative satisfies that equation? That's what we're trying to solve. Okay, now you may not notice it, but your brain does. This is separable, right? I see a common y term, so let me factor it out. Nice. Okay, we have now separated it into a function of x times a function of y, so I know to solve this, to find implicit solutions, I just need to compute these integrals right here. Okay, now, as we did before, we'll do the integrals and only include the plus c on the right-hand side. So, the integral of 1 over y squared is negative 1 over y, right? The integral of 1 over y is the special case. Y to any power, when you integrate it, right, you're going to add 1 to the exponent and divide by that new exponent. The only time that's a problem is if the exponent is minus 1. That's where log comes in and saves the day. Okay, so but for us we get this. Now here we go. We have again an implicit solution, and I can make it explicit. So let me do that. But before I do that, we do want to be very careful about how we go about solving for y, because it's very easy to make some rookie mistakes right now. Okay. All right. So let's address some things that we want to be careful about. So we have this. First thing I want to do, let me multiply by minus 1, both sides of the equation. Okay. So the right-hand side becomes 1 over y, the x squared goes negative, the 4x goes positive, and note the constant abuse continues. Alright, so now I want to solve for y, and we want to be very careful what we're about to do here. This means I need to cross-multiply. Right, a very common thing that a lot of people will do here is go, oh, I know what y is. Y is equal to negative 1 over x squared plus 1 over 4x plus 1 over c, and that's totally bogus. That is not how reciprocating works. I need to cross multiply. In other words, this term is going down here, and this term is going up here. So I've got y is equal to 1 over the entire entity. We cannot fraction separately. Okay. And then just to make it look a little nicer, we can change the order, get 4x minus x squared. If you really want to go crazy, you can factor an x out here. And now that we've solved it, you of course now, after solving it, will plug this in the Wolfram Alpha and check your work. And it is worth noting, I did that. They actually factor out a negative x out of this, and so they've got c minus x times x minus 4. It really doesn't matter. When it comes to getting solutions, make them look as nice as you possibly can. Don't go crazy, right? The last thing you want to do is get the right answer, and then when you start simplifying, make a wrong answer. It's like the worst thing to do. Never do that. But we'll pause it right there and say that's good enough. All right. Well, that was a lot of fun. How about another one? Okay. So now's a good time to mention something. If you haven't been doing it, while you're watching these videos, you should be watching these with pen and paper next to you. You should be writing while you're watching. And because this is pre-recorded, you can pause whenever you want. So you can go at your own pace. And I know for a fact you've got this video on 1.25 speed, probably. So don't think I don't know you're doing that. But anyway, now is a good time. Now is a great time to pause the video and solve this problem on your own, and then see if your solution matches up with the one I'm about to do. Okay. All right, so feel free to do that. If you've rejoined us right now, let's go ahead and solve this separable differential equation. Right, note it's an initial value problem, so we are going to need to get rid of that c that shows up when we solve this problem. All right, so let's get going here. So what's the first thing I'm going to do? Well, right, we want the right-hand side to be a function of x times a function of y. And again, maybe at first glance, this thing does not look like a separable equation, but it is. So the first thing I'll do is multiply both sides by e to the x. I'm going to isolate my dy dx. Right, as we were talking about in our first theorem, the existence uniqueness theorem, every first-order dE, you can just isolate the derivative and throw all the other terms on the right-hand side. Now, it's worth noting that we'll have some ramifications, which we'll get into later on, but for now, multiply both sides by e to the x, so I get this, and then I see a common y term, so let me factor it out. Here we go, we've got my function of x times my function of y, so I know that now I need to compute this. So I've got some integrals to do. Now, 1 over y is going to be log of y. We already know that. The integral of negative sign is going to be positive cosine. Now, e times e to the x, now that integral, if you want to do that one by hand, you need to do an integration by parts. The purpose of this class is to not bury you with integrations, so we're going to avoid looking at problems that have, like, sufficiently crazy integrals, like what's the integral of, like, secant cubed, or something like that, but it's impossible to avoid integrals when you're solving differential equations, so we are going to run afoul of a couple of ones that are going to require some techniques that you learned in Calc 2. So e times e to the x, that's an integration by parts. You can check on your own that you should get e to the x times x minus 1. Right, I've already done some factoring. If you really worked it out, you get x times e to the x minus e to the x, but I did some factorization already. So there's going to be a couple of times where I'm just going to say you can do this integration and get that. If it's an integral that really needs a discussion of the technique, we'll take a moment. But for the most part, right, I'm not here to crush you with integrals. If this was Calc 2, that's what I'd be doing, but this is differential equations, right? They're part of it. You know how to do these integrals. I'm not going to kill you with them, but we will run into some integrals that are going to require some techniques. So, and side note here, it's worth noting, e times e to the x times e to the x is an integral. You should probably have at the ready. It actually does show up quite a bit in differential equations. All right, but anyway, boom, here we go. We've got now an implicit solution. It's worth noting I can make it explicit if I wanted to. But I've got a nice implicit solution. Now, I'm not done. It is an initial value problem, so I do have an initial value. And I want to warn you about something. Plugging that initial condition in now, x is equal to 1 and y is equal to -1, will give us this. And you better notice that something is wrong. Log of -1 is a problem. Right, that is undefined. Log of negative numbers, we cannot do that. We'll get an answer to that a little bit later in the class. But, so what went wrong here? Well, remember what I said earlier. When we do the integral of 1 over y, for the most part, we can just say it's log of y and move on with our lives. But here's a situation where you would really have needed that absolute value in order to make things go the way you wanted them to go. Alright, so what's the fix? Do we need to include the absolute values? Well, no, we don't, and I'd prefer not to, because in my opinion it just complicates the matter. So what's the fix? Well, the fix is that when you are trying to plug in an initial condition, we're going to want to do that after we have made an explicit solution out of the implicit one. Okay. Now, in the cases where you can't make an implicit one, then fine, put in the absolute values and, all that other stuff. But for this class, for the things I'm going to ask you to do, for the things we're going to work on, just don't even worry about that. Anytime something like this will show up, it's an implicit equation that can be easily made explicit. So do that first before plugging the initial condition. Okay. So let's do exactly that. Exponentiate both sides, and that gives me this very fun equation. So note, again, constant abuse. Okay. Alright, so, this is just noting some minor things that we need to be careful about while we're doing things, right? We're making decisions to make our computational life easier, and we want to be aware of that as we go forward, so just something to keep in mind. So pay attention to initial conditions, by the way. This is also indicating that certain initial conditions might make your differential equation very unhappy. Alright, but we're able to get around this, and we can get to here. Okay, so now that we have the explicit solution, now let's plug in the initial condition. So y is -1, x is 1. So e to the 0 is 1. Cosine of 1 is something. Who cares? It's a value. It's there. So we can solve for c now. It's just negative e to the negative cosine of 1. And therefore, the unique solution to the initial value problem is that beautiful solution right there. Okay. Yeah, look at that function. That's a good one, right? Yeah. Not too bad. Alright, so there we go. We have solved now an initial value problem using the method of separable differential equations. Not the worst thing in the world. Not the most beautiful solution, but it's there. It's out there. We got the answer. And then now, if you wanted to do a little bit more analysis, we've got an explicit formula that we can use and work with. So, that's good. But alright, that is it for today. So, separable DEs, we know what to do. Sounds good. Alright, I'll see you next time.